In this video, we're going to take a look at one more thing that can happen when you're trying to graph a rational function. We're going to start off the same way we did yesterday, though. Taking a look at a function, k of x is x squared minus x minus 6 over x minus 2, and go through our 4 steps: asymptote, asymptote, intercept, intercept. See what we can get done. And then remember, we have a backup plan. If we need to, we can always plot extra points if we need to. That's our overall plan. Let's start with the vertical asymptote. Now, we saw these yesterday that when we have things that need to be factored, a lot of times they get simplified. So I'm always going to take a quick look at the simplified version first to see if anything cancels. So we're going to factor out that numerator. X squared minus x minus 6. Well, that does factor. X minus 3 times x plus 2. But that does not cancel out the x minus 2. X plus 2 over x minus 2 do not cancel. There's nothing else you can do here. It's worth pointing out we do have a domain restriction. X can't equal 2. And we can use that domain restriction to say, oh, well, that's the vertical asymptote. X cannot equal negative 2. So if x cannot equal negative 2, as x gets closer and closer to 2, the denominator will get smaller and smaller and smaller, which means the fraction will get infinitely big, or of course infinitely negative. So let's graph the vertical asymptote that we just identified at x equals 2, and then move on to our slant asymptote. And this is where you say, okay, well, that's no problem. We have two possibilities, right? Either the degree of the denominator is stronger than the degree of the numerator, or the degrees are the same. Wait a second. No, in this case, the degree of the numerator is stronger than the degree of the denominator. So this is a third possibility that we didn't mention yesterday. This is actually not going to make a horizontal asymptote at all. This is going to make what's called a slant asymptote, also known as an oblique asymptote. It's not a very complicated process. It's very similar to what we do when the degrees are the same. We just divide. The only difference here is we're not going to just divide the lead coefficients like we did in the last class's examples with the horizontal asymptote when the degrees of the numerator and denominator are the same. When the degree of the numerator is bigger, we're going to do the division. Do x squared minus x minus 6 divided by x minus 2, but luckily we get to just completely ignore the remainder. So that's going to be our strategy here. So that's what we're going to do. We will divide and ignore the remainder. I have the graph already here. And so in this particular example, synthetic division would work just fine too. So either synthetic division or long division, whichever you prefer. Just remember, had this been a higher degree denominator, we wouldn't be able to use synthetic division anymore. Because I have the long division set up, I guess that's what I'll do. Remember the process for long division: divide, multiply, subtract. So I'll divide x squared divided by x is x. I will multiply x times x minus 2. So that x squared minus 2x goes there. And then we will subtract x squared minus x squared cancels. And negative x minus negative 2x is positive x. I'll bring down the minus 6. And then we start again, divide. And you know what? That's all I need, because everything else would be to find the remainder. I don't really care about the remainder. I'm going to stop here. So my slant asymptote is the line y equals x plus 1. And from what we know from way back in Algebra 1, y equals x plus 1 is a slanted line with a slope of 1, a y-intercept of 1. So I can graph that. Actually, I have it here. I just need to drag it in. Start with that y-intercept and a slope of 1. And there's the line y equals x plus 1. And there's my slant asymptote. The slant asymptote works the same way as a horizontal asymptote. As x approaches infinity, the y value will approach whatever the slant asymptote is approaching. In this case, this slant asymptote, it's a line with a slope of 1, it's going up. So the f of x will also approach infinity. It'll get closer and closer and closer to that slanted line. And as x approaches negative infinity, we're going to follow the course of that arrow. So f of x will approach negative infinity. Just like the horizontal asymptote translates to the end behavior, a slant asymptote does also. Our next steps are the same as they were in our last class. Remember, we've got our asymptotes. We sort of have the shape of our graph set up pretty well. But now we need to figure out exactly where our graph is going. And that's where plotting some points, starting with the intercepts, comes into play. So actually, okay, so that's the same graph I had above. So we're going to find our intercepts. We can start with the x-intercept. I'll start with the y-intercept because it's easiest. F of 0, and this is going to require me to scroll back up because I've already forgotten what the equation is. I'll just bring it down with me. So f of 0, I can certainly look at the factored version if I wanted to, but there's no real reason to for the f of 0. I can just ignore all the x's and say that f of 0 is negative 6 over negative 2, which is 3. So that means I have a y-intercept at 3. And my x-intercepts, here the factored version is going to be useful. Remember, k of x was x minus 3 times x plus 2 over x minus 2. And to find the x-intercept, we find the zeros of the numerator. So when does x minus 3 times x plus 2 equal 0? Well, we know this from the factor theorem, from split and solve, from the zero product property way back in Unit 3. We know that we can say that x minus 3 could equal 0, or x plus 2 could equal 0. And so our two zeros come from those factors. Most of you are probably able to get that without even writing it all out the way I did. So our two zeros are x equals 3 and x equals negative 2. And we will use those two to plot the entire graph. In this case, I'm not even going to need any extra points. From this x-intercept, this one, heading back towards negative infinity. I started with that one because it's all the way on the left, and I'm going to talk about the end behavior on the left. I know that my graph is going to follow the slant asymptote. But as the x value gets bigger, it's going to pass through the y-intercept, and then because of the vertical asymptote, it's going to be the graph is pulled upwards. And I can make this line a little bit thicker so we can see it better. But this is what's happening on the left. On the right, I have this x-intercept. I know as the x gets bigger from this point on the right, it's going to have to shape itself towards the slant asymptote. And as x gets smaller, as x is a little bit less than 3, it's going to be dragged down by the vertical asymptote. And so there's your graph. One thing I want you to note is we said when we did the slant asymptote, we said that the graph was basically y equals x plus 1 with a little bit of a remainder. And what that means to say the graph is basically y equals x plus 1 is if we take a look at this, it was x squared minus x minus 6 over x minus 2. So this does look exactly like the graph that we have down here. So you can see those two graphs do match each other. We have the same x-intercepts, the same y-intercept, the same vertical asymptote at x equals 2. So there's my vertical asymptote. Zoom out, you can see a little bit better. But when we keep zooming out and zooming out and zooming out, you can't even really see that vertical asymptote so much anymore. It's just a temporary little blip. And if we graph the line y equals x plus 1, that was our slant asymptote, you can see that our slant asymptote and the function, like, you can't even really tell the difference between them. That's the idea of the asymptote. If you do the division and ignore the remainder, what you have is the graph that our red function, it's pretty much y equals x plus 1. It's just that when you get like right near that vertical asymptote, things change. Because only when the x is close to 2 does the remainder really matter. Other than that, the graph is pretty much just this green y equals x plus 1. When we do these on paper, you're not really going to zoom out and see the sort of the end behavior. You're going to like focus in on that vertical asymptote. It's going to make a prominent feature of the graph, and that's fine. But it is important to understand this idea of like what the slant asymptote really means to us. It's this zooming out. The slant asymptote pretty much is the graph, except for like a little bit of like a moment in time here.